Hello guys, how are you? In this video we're going to continue our lessons, and today we're going to start with section 5, molecular geometry. Here guys, we're going to talk about the structural formula and what is the shape of the compounds in the 3 dimensions. This is why we're going to start here with Vespers theory, which states that repulsion between sets of valence level electrons surrounding an atom causes these sets to be oriented as far apart as possible. And actually, Vespers theory, it is an abbreviation of valence shell electron pair repulsion. So Vespers is V for valence, S for shell, E for electrons, P for pair, and R for repulsion. So mainly we are talking here about repulsion between electrons, which is something natural, because as you know, the electrons are all negatively charged, so they have to repel each other to be stable. And this repulsion actually is the main factor that affects the shape of the compounds in 3D. As you know, the structural formula can show us, as we said before, the shape of the compound in 2 dimensions, but not in 3 dimensions. So here we're going to use this theory, which is talking about repulsion between electrons, to predict the shape of the compound in 3D. As a start, we will start with the basic compound BeF2, which is beryllium connected with 2 fluorine atoms. As you can see here, this is the Lewis structure for BeF2, and as we know, Be is an exception from the octet rule, so beryllium will not fit the octet rule. It is enough for it to be surrounded by 4 electrons. So simply, as you can see here, beryllium is connected with 2 fluorine atoms to form a linear shape, as we can see here. We will consider beryllium is the blue ball here, and each yellow ball is fluorine atom. So this is the shape of BeF2. It is a linear shape, and the degree between atoms is 180 degrees. Because simply the atoms will be as far as possible from each other to repel, to decrease the repulsion between the electrons here at this fluorine atom and the other fluorine atom here with the electrons of the bond here. So this is the shape that will give the minimum repulsion between electrons in the compound. So this is the shape of BeF2. What about another compound, for example, BeF3, as you can see here. As we said before also, B is an exception and it will not fit the octet rule. It will be enough for it to be surrounded by 6 electrons. So simply, the most suitable case and scenario for distribution of atom around the central atom is this shape. As you can see here, by making the degree between the electrons here 120 degrees, this is the minimum repulsion between electrons, because if the angle here was closer, so the electrons here and here will repel each other. So they will push each other to the other side. And if this bond and this arrow moved closer to this side here, it will getting closer to this one, so this one will push it again to the other side. So this is the shape that will make the wanted balance of repulsion forces between electrons, which means this is the most stable case for this compound. So, guys, here, you know what I'm talking about when you go to the book and read the book. When we talk about BeF2, we will represent of the Be, which is the central atom, by A. So A here will be the central atom, and B here is the surrounded atom. So AB2 means BeF2. So if you have any compound with this general formula AB2, that means that the shape of this compound will be linear shape according to VSEPR theory. So assume that we have, for example, CaCl2. According to Lewis structure, this is Ca, Cl, and Cl. Here we have 7 valence electrons. So it is A with B and B. So the general formula here is AB2. And AB2 means that we have a linear compound with an angle of 180 degrees. And if we're going to talk about the shape here, this is, for example, the central compound, and excuse me because I'm using only one hand. So this compound, the central atom, this atom will be bonded to this is the central one. It will be bonded here to another atom, and the second one will be at this side. So this is shape, as you can see, it is linear shape, and the angle between the arrows is 180. While, for example, if we have AB3, one atom will be at this side here, and the other atom will be at the other side here. So this is the shape of this compound, which is AB3. I hope it's clear for you because I'm using only one hand. So this is AB3, as you can see, which is here. Which is triagonal planar shape. So the geometry for AB3 is triagonal planar, and for AB2 it will be a linear structure. What if we have AB4? Like, for example, CH4. Remember, guys, that when we talk about, for example, CH4, this is CH4. This is carbon, and we have here H, 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 and H. Now, if you look at the shape here, in 2 dimensions, you will think that this is like a square or something like that. But when we talk about the 3 dimensions, it will be something different. Because as you can see here, the angle between electrons here, these electrons, this is 90 degree, and here it's also the same 90 degree and 90 degree and 90 degree. Okay, this could be acceptable for the 2 dimensions, but what happened actually in the 3D? Do you think that we could have another structure that will give us minimum repulsion forces between the electrons? Actually, yes. Let me just prepare the shape here. So instead of having a square shape with a degree of 90 degree, we will have this shape as you can see here. As you can see, the red one is the carbon, and the 4 H's are around the carbon with this shape, which we called tetrahedral. No matter how you change the shape of it, it will be always symmetrical, and it will be always have the same shape as you can see here. But we can't draw this shape in 2 dimensions. So if you have a general formula with A, which is the central atom here, with 4 atoms around the central atom, you will have a tetrahedral shape, which is this shape as you can see here. So this is the tetrahedral. You can flip it inside. We will have always the same shape and the same angles. It is a symmetrical shape. And the angle between the atoms will be, as we can see here, 109.5, like methane. So first, guy, to be able to predict the shape of the compound in 3D, you will have to draw the lowest structure first, and then you can determine the shape for the compound. So if we have, for example, this example here, use VSEPR theory to predict the molecular geometry of boron trichloride BCl3. So B contains 3 valence electron and the chlorine 7 valence electron. We will have the shape here as you can see. This is how we draw it by Lewis structure. So here the general formula for this compound is A, which is B, and B3, which is a chlorine. So AB3 will be trigonal planar structure. So we will have trigonal planar shape. What about this one? HI. Now when you have only 2 atoms, it is very clear that you will have only a linear shape. What about here? We have CB4. Obviously it is AB4, so it will be tetrahedral. And here, if you have this one, CH2Cl2. Now we have 2 atoms of hydrogen, with 2 chlorine atoms. So it doesn't matter if the atom's identity is changed. Finally, we will have one central atom with 4 different atoms around it. So we will have also AB4. So the shape of this compound will be tetrahedral. This is the first point of our lesson today. Here we are talking, guys, about the compounds with no non-shared pair of electrons, which means, as we said before, that all electrons available are already shared and forming a bonds inside the compound cell. So we don't have unshared pair of electrons, like, for example, what happened when we talk about NH3. NH3, as you know, nitrogen contains 5 electrons, and we have H with 3 times 1 electron equals 3. So the total is 8 electrons. So we'll start with NH. H. So we consumed already 6 electrons. So we still have 2 electrons. And those 2 electrons finally, because hydrogen will not accept any more electrons, so we will put the electrons here. Now in this shape, you could think that NH3 is A, B, 3. So it will be like this one, H. H and H. But what about the non-shared electrons here? If we draw it again, we will have N, H, H, H. And you could think that this is triagonal planar, and the most suitable case here, the most suitable location for the electrons is here. But if we put the electrons here, don't forget that here we have electrons and we have electrons here, and finally we have electrons also here. So repulsion forces will happen between this shape, between this bond and this bond with this pair of electrons. So what do you think? Actually, what happened is just similar to this is, imagine that this is the triagonal planar, but because we have a pair of electrons located here over this atom, this electron will cause this electron to move far away from it. Same thing, same case with this shape, and same case with this bond. Because finally we have repulsion between the electrons here and the electrons of the bond here. So we will have this shape. As you can see, it is not a tetrahedral because we don't have a bond here at this side, but also it is not a triagonal planar, but it will be triagonal pyramidal, because we have 3 bonds with 2 electrons in each bond, with an atom around the central atom, but we have unshared pair of electron here that will cause repulsion with the bonds here and push them together. And remember that, guys, we are talking about 3 dimensions here, which is something different than the 2 dimension. So we will have the shape finally. So this is what happened when we talk about ammonia molecule, which is NH3. We can see it here. So existence of electrons here in this side will cause repulsion with the electrons here and push them down to make the angle 107 degree between each other. So we will have this shape, which is triagonal pyramidal. So in this case, because we have one valence electron here, now the general formula for this compound will be A, which is N, the central atom, with B3, B is H, the 3 atoms, and we will symbolize the electrons here by the symbol E. So we will have here A, B3, E means one valence electron. So if you have a general formula for a compound with AB3, E, the shape will be pyramid with triagonal base. What about water? Now, we used to draw water as O, H, H. But don't forget that we have 2 valence electrons, 2 unpaired electrons on oxygen here and here. And this pair will repel the bonds here. And also, they're gonna to repel each other. So in this case, we will have, imagine this shape. I'm gonna to remove this bond here, and instead of it, we will put, I think you can guess, we will use electrons instead of it. So this is water. This is the oxygen atom with 2 pair of electrons here and here, and here we have the hydrogen. So as you can see, this is the shape of water. It is not a linear shape, but it is angular or bent. Of course, as we said before, when we draw the Lewis structure or the dot structure, we put the electrons. But if we're going to draw the Lewis structure, we have to remove the electrons from it. So finally, we will have this shape, which is angular or bent shape. It is not a linear shape because the electrons located here will push the electrons of the bond away to make repulsion as less as possible and form the most stable structure for H2O. And here the general formula will be A, B2, E2. A, when we're talking about the central atom here, and B2, the 2 atoms here, hydrogen and hydrogen, and E2 because we have 2 pairs of electrons. So guys, this is a table that will give us the whole information. The most important thing here, remember that when we talk about the general formula, So if we have AB2 formula like BeF2 or CaCl2, we will have a linear shape. If we have AB3, like for example PF3 here, we have no valence electrons, no unshared electrons, then we will have triagonal planar. If we have AB2 like this one, but with one pair of unshared electron like NH3 or NOF here, as you can see here, that means that this valence electron will push the linear bonds downward to decrease repulsion. So we will have pent or angular shape like water, H2O, same thing. If we have EB4 like CH4 here, we will have tetrahedral shape. And if we have AB3E like NH3, then we will have triagonal pyramidal, as we see here, as we explained in H3. And if we have AB2, E2 like H2O, we have two pairs of non-shared electron. They will cause repulsion and push the bonds to the other side to decrease repulsion, so we'll have pent or angular. I hope guys that you just focus on these shapes. Of course, we have here another examples, like when we have AP5, we will have triagonal bipyramidal, or if we have CF6, this shape here, then we will have an octahedral shape. Hope that you get it. And you just, as I said before, you just have to focus here at the general formula. So, I'll repeat it again here. If we have A, B, or A, B2, then you will have a linear shape. If you have A, B, 3, you will have triagonal planar. If you have A, B, 4, you will have a tetrahedral shape. And remember guys that here we don't have any pair of non-shared electrons. So here we have HI, for example, or we have BeCl2. And when we're talking about non-shared pair, we mean non-shared pair over the central atom. Because, for example, when we're talking here about like Be with Cl and Cl, we have an unshared pair of electrons here over chlorine. But chlorine is not the central atom. So the main, when we say non-shared pair, we means over the central atom here, we don't have an unshared pair. So let's go back here. This is the cases here. Now, the other cases when we have an unshared pair of electron, like for example, A, B, 3, E, like in H3. This is the shape of NH3. We have a pair here. This is NH3. We have no shared pair of electrons here. So the shape here will be triagonal pyramidal. Or if we have A, B2, E2, the shape will be angular or bent. So existence of non-shared pair of electron will cause repulsion and pushing the bonds away from the non-shared pair of electrons here. This is why we don't have HOH. It is not a linear shape in the H2O because the electrons here will push this bond away and the electrons here will push this bond away. So finally we'll have OH. This is all for our lesson today, guys. Hope you get it. And we just focus on shapes that we studied here. And just remember the general formula. Or what it matter actually, the central atom, how many atoms around the central atom, and how many unshared valence electrons we have or exist in the compound. Thank you and be safe.